So with this melted material, which remains chemically the same unless there is some sort of mixing, this material will now physically be much different than it was before, although it remains chemically the same. The material will be more liquid and it will be hence less dense. So something that is more liquid and less dense, or not necessarily more liquid, but definitely when it's less dense, tends to be more buoyant than the surrounding whatever it is. So in this case, the surrounding rock, the surrounding material. So when it's more buoyant, it will rise towards the surface of whatever medium it's in. In this case, it is magma that is rising towards the surface as it's less dense and more buoyant than the surrounding rock. So the magma is rising towards the surface. So a good analogy for buoyancy that you can think of is oil and water. So the oil would represent the magma that you're seeing here, and the water would be the remaining rock material that is surrounding it. So oil, as we know, is less dense than water, and so it will tend to rise above the water onto the surface. Same thing happens here. The magma is less dense and more buoyant than the surrounding rock, and so it will tend to rise upwards towards the surface. So if this magma cools enough to crystallize, so crystallization is also known as becoming rock, again, cooling enough so that it becomes rock. So if the magma cools enough before it crystallizes, meaning before reaching the surface, it becomes an intrusive igneous rock. So this can be seen, for example, in this conduit over here. So if this conduit cools enough before it reaches the surface, it's going to become rock. It's going to be made into rock here at depth, right? And so that's going to make it be an intrusive igneous rock, is what we call them. But if, for example, that magma is able to continue its way towards the surface without cooling, and then once it reaches the surface, it erupts, then it becomes an extrusive igneous rock. So once it erupts and then it cools at the surface, it gets made into rock at the surface, then it's called an extrusive igneous rock. So again, if it cools and is made into rock below the surface, it's intrusive. If it cools outside and is made into rock, it's an extrusive igneous rock. And again, being made into rock from something that is molten is called crystallization of that magma. So once you have this possible ongoing volcanism, right, so this set of eruptions, you tend to get mountain formation, okay? So just like you're seeing over here in this example, as the magma rises, material gets pushed upward before it erupts, and this causes many of these volcanoes to also rise, or to also see material rising next to them. So you get mountain formation with volcanism typically. And so this is what we see, for example, in the Cascade Mountains. Not every mountain in the Cascades is a volcano, although there is a lot of volcanism there. So this mountainous formation that occurs typically has a lot of material, and this material, when it's exposed to the surface, is going to be subject to surface processes like weathering, like transport of the sediment through water, through wind, through ice, or through gravity, and further on to deposition of that sediment. Okay, so if, for example, again, those mountains formed, and now much of that material that used to be below the surface is now exposed to the surface, weathering agents like water, like wind, like ice, like other chemicals floating around may weather the rock away, and then the transport agents, which are water, wind, ice, and gravity, will move that sediment elsewhere. Okay? So these surface processes that we have are only possible with the help from the remaining 3 cycles, of course. So again, it wouldn't happen, those surface processes, they wouldn't happen without the hydrologic cycle, the biogeochemical cycle, or the rock cycle. So they're definitely needed for that final event to occur. But you see how after there has been transport of that material, right? So once that has been eroded, basically, we go back to the first step, which is the sediment deposition. So once that is moved outside, it's going to go back to being deposited somewhere along the riverbank, delta, further offshore, so on and so forth. So it is a cycle. This is just one of the examples of the tectonic cycle. There are many other types of examples that can happen from the tectonic cycle, but it gives you an idea of how these things happen and how the tectonic cycle doesn't act by itself. It needs the help from the other three cycles for all of these events to occur. So we can see that only from the tectonic cycle a number of natural hazards are directly caused. If you were thinking of any of these three natural hazards that I have pointed out down here, as I was explaining the tectonic cycle, then good for you. You've done a very good job already. So yes, earthquakes and volcanoes are pretty much only caused by the tectonic cycle. Tsunamis, on the other hand, also have to do with the hydrologic cycle, but are mostly just under ocean earthquakes that occur, and because of the water that is in the ocean, they get that extra help. So those three natural hazards are mostly caused by the tectonic cycle. So with these different plate boundaries that we have, there is a friction that is being created between the plates. So there is this force that is, making things rub against one another or move away from one another, which still creates friction further below, or sliding past one another, which definitely makes things uncomfortable. So when you have this friction, when you have things sliding past one another, like we see in the San Andreas Fault, for example, or in the Andes Mountains, for example, when things are coming together towards one another, you will get a redistribution of the material. So when you get this redistribution of material, things move from place to place, you typically will see volcanic activity taking place as well. So like the one that you see again in the Cascade Mountains, when things are coming towards one another, some of the material, sure, gets destroyed down here, but some of it gets created once you get up here. When you have divergent plate boundaries, if things are going away from each other, this material is getting moved further apart, so some material has to come and replace it. And when you have things, rubbing past one another, sure, you don't get material created or destroyed, but it does get reconfigured. It gets moved from location to location, and many times this causes a change in the material. So many times you get metamorphism, for example, in the rocks that are near those locations. All right, so here's the second cycle that we'll look at, and that is the rock cycle, which is highly tied to the tectonic cycle. That's why you see the same image over here, but with a few different labels. So the rock cycle is split into three different types of rocks, as many of you probably know. So those three types of rocks are going to be igneous rocks, sedimentary rocks, and metamorphic rocks. Okay? You may have already learned some of these types or even some specific rocks from each type, but I'm still going to go ahead and go over some of the aspects from them. Okay? So let's start with igneous rocks. So igneous rocks are subdivided into two main types, as I had said in a couple slides ago. So they're subdivided into intrusive igneous rocks and extrusive igneous rocks, also called plutonic and volcanic igneous rocks, but you don't need to know that part necessarily. So they are determined based on where the magma crystallizes to become solid rock. So whether it crystallizes below the surface or above it is what makes the igneous rock be intrusive versus extrusive. So again, if the magma, which is the principal material which makes up the future rock as it crystallizes or cools to solidify, is below the surface, or meaning it crystallizes below the surface, then the rock is an intrusive igneous rock. If the magma reaches the surface as lava, so once it reaches the surface, it is lava, and it either erupts violently, like ash or bombs as we call them, or it flows nicely on the surface, for example, like the Hawaiian eruptions, then once that lava crystallizes, it will result in rocks that are called extrusive igneous rocks. Okay? So those are the two main types and how they crystallize and how they are named. Sedimentary rocks are the second type of rock that we'll look at. So sedimentary rocks are found at the surface or near the surface, meaning somewhere in the first few kilometers of the crust probably. They form from previously existing rock at the surface that got weathered, it got eroded, and later it got lithified into another rock. So I know that all of those terms, weathering, erosion, lithification, you may not be familiar with right now and may go right over your head for right now, but you can think of sedimentary rocks as rocks that are made up from pieces of other rocks, which got broken up into smaller pieces, and they got moved from their initial location, and then they got their new place of deposition where they started fusing together by compaction and cementation. So all of those pieces from other rocks were made small, they got moved, and in a specific location where they got deposited, they started fusing together by compaction and cementation. Okay, so again, this is super oversimplified, but for now, it's enough to understand the basic of it, and it's enough for what you'll need for now. We'll cover some sedimentary rocks in detail, like sandstone, shale, limestone, as we go through the course later on, and as we go through the different natural hazards that affect them, or that are being affected by the type of rock. Okay? Okay, and then the third type of rock that we have are metamorphic rocks. So metamorphic rocks are usually created at depth, somewhere within the crust. So at depth is a very important concept to have here. Not always, but most typically they are created at depth. So these come from previously existing igneous, sedimentary, or even from other metamorphic rocks which are exposed to high heat and high pressure. Okay? So high heat and pressure is what rocks need to become metamorphic. And again, because typically high heat and pressure come with depth, that is where we usually see the creation of metamorphic rocks. This doesn't always happen. So for example, in instances when you can get a combination of high heat and pressure to create a metamorphic rocks closer to the surface, you can also have that. So for example, when you have an impact, so some sort of extraterrestrial impact, that impact, or some sort of asteroid or comet or something like that, the impact from that body onto the surface will create a lot of heat and a lot of pressure, and so metamorphic rocks can happen at the surface in those instances. But it's hard again to get heat and pressure combined in other locations. So that is why we typically see metamorphic rocks being created at depth. So the high heat and pressure causes the previously existing rocks to be a lot more plastic, so a lot easier to deform and to mold into new rock. So you can think of, for example, Play-Doh. So if Play-Doh is hot, it's easier for you to maneuver it. If it's too cold, then it's going to be a lot more solid and a lot harder to maneuver and mold. So once the pressure and the heat are no longer exerted onto the rock, then it is there for us to discover it, okay? So it already got molded into something else, and it's finally a new rock, and it's there for us to discover it. So metamorphic rocks are the least abundant type of rocks that we have on the crust, and certainly the least abundant at the surface for sure. So because many of them are created here at depth somewhere, it's going to have to be a lot of time before they rise up to the surface and for us to see them up here. So a lot of vertical movement needs to occur in some sort of mountain building event for us to see them. However, we do have them. So for example, here in Idaho, we have a bunch, or not a bunch, but a fair amount in the Sawtooth Range, in the Pioneer Mountains, and then further down, I think by the City of Rocks, we have some too. So we do see them, just not in the abundance that we see sedimentary or igneous rocks. So overall, Sedimentary rocks are the ones that are most common at the surface. They make up about 75% of surface rocks, but igneous rocks make up the greatest majority of rock overall in the crust, which make up about, I think is 90% or so. So most of them lie below the surface, most of the igneous rocks, and definitely most of the metamorphic rocks also lie below the surface. Sedimentary rocks tend to be at the surface or near the surface.